again, students today are going to 12.1, which is study kinetic action. We're in one, study kinetic reaction rates. Very recent over reaction, and this day is lessons in real life, in the rate of a particular reaction. So, if we were in Canada in time, if the board behind me, I would have done this lab on April the 24th. For honors, we would be past that. After that, of course, we're not now anyway doing learning to the updated house calendar that was home. I can't in the part of May. I believe honors. I said I'm not sure given time that we left that we would given the average. Important unit kinetics in regard to need to have your next, whether that be chem or your freshman level chemistry class. It's material review and whether that and so we get to the topics for you, and I hope that yourself to go ahead and learn and get advantage of that. Lab is here. There I am, and now got some preliminary work on this one. So there's our so we're going to go through setup for this, and then we'll actually I'll perform it with you, and then we'll the kinetics of a reaction. The reaction is called a clock reaction because of the means of the rate. Day one, and I mentioned on day one back in August, we actually also react towards two solutions back and forth, and I think they were either both or one was maybe cloudy color, but after time, the sun turned a very dark brown color, which is the end of the reaction, or that the reaction had completion. It was also a clock reaction, as is this one. We use clock, so to speak. This particular action involves the elimination of according to the net ionic. So here's acetone, E3, called pro, or they'll remember into acetone for propanol. We iodide, and we get the formation of three products. The reaction, the hydrogen ion concentration in the solution, HCl is in this solution, which makes it acidic, which acts as well as the concentrations of acetone is listed here. So the rate is equal to K times acetone or propanol power reaction. The iodine concentration rate times by ATL based to some three factors that we're going to determine the So the value either will be determined experimentally, as well as the magnitude and unit of the rate constant as well. Go through quickly before we do preliminary work. So we have right here, we have hydrochloric acid. We have water, which is going to act as our volume equalizer. I'll explain that. Being constantly stirred, I two sides. What's the halogen element that is a solid at room temp, standard pressure, and it's not very soluble at all. Believe it or not, let's see, 15 a.m. And when I got here this morning at 6, I started, and I put the iodine in water and started swirling it, and I still see iodine at the bottom. They're flipping, but they are not. It's not soluble. Excuse me, it's not. And so stirring now for over 5 hours, and it is now saturated. I don't know that any more than it dissolve or not for it there. This filtration. Like I said, these three here are in our, and then water is the volume. We'll talk about that here in a little bit. So basically what we're going to do is we're going to the quantities and the trends of each of these in several experiments, and then based on do that, we're going to be able to isolate and determine a reaction for each, which gave us our rate law. So before we do that, data table, we actually have data. Here's our procedure, and so in reaction 1, we're going to take 5 mLs of solution, and to that we're going to add mLs of water. So if you add that, 5 mLs of solution. We're going to use of acetone, 5 mL each of each, and this time only 5 mLs of water. And now explain. So here we have 5 and 15 mLs of our 3 reactants. Water make 25 total. We have 10, 15, 20 reactants, but we want the volume of the solution to be the same all through. Very important. And so instead of 10 water, we only have 5, 10, 15, 20, grand total 20 mLs of water. Section 3, we have 5 mLs respectively of our 3. Again, 5 mL water, bring 5. In action, we have 5, 10, and 10 mLs of water. We already 25 mL, we don't water. And then reaction 5, our last, we 7.5 mLs of the 3 reactions, and thus then we mLs of water to equalize the volume. So as you use volume, you can kind of see how we're laying out so that we determine the reaction order for each reactant. For instance, and I'm not jumping the gun, I just want you to be thinking about this as you finish up on your all the procedures. So look in reactions 1 and 2. In reactions 1 and 2, we beat the volume of acid, whereby we left the volume of HCl and the volume of IU constant. It should. Other two reactants constant, then we would be using reactions 1 and 2 to determine the reaction order for acetone. Remember the reaction order for acetone, you want to make sure the reactants. Okay, so based on that, we use 2 to determine order for acetone. And as you look at the other combination of reactions, 1 and 3 or 1 and 4 or 2 and 4 or whatever, you should determine of reaction that you would use isolate and for yellow and for iodide. Okay. Go down the data because we determine reactors are concentration. These are right. So remember, we want concentrations. We're in. All right. This says data to just concentrations. Here's what I mean by that. So our acetone out of the bottle here is molar, 4.0 molar. All right. Down here, adjusted concentration at 0.0. I want why that is true. So we go back up here. Our acetone, that's all there is in there, so its concentration is 5 molar. And you 5 mLs of HCl and 5 mLs of iodine and 10 mLs of water. We don't want 5 mLs to be more. We have a total volume of 25 mL. So the number of moles that's here has been by a factor of 5. All right. It's molar, which is just the of acetone. When you add all this, the other reactants, that total volume anymore. It's 20. Okay, so now we're going to go back to the front page and take a look at the procedure. Now that we have all of our adjusted concentrations, as we mentioned just a bit ago, that we will use then in determining our rate law, in particular our reaction orders, and then ultimately our rate law. So as I go back here to the front page, of course we've got a lot of lines and numbers in there. Just kind of ignore those. You can look at your own paper. So we have our reactants here. Here's our 4 molar acetone and our 0.5 molar HCl, and or I should say our 1 molar HCl. Sorry about that. And then we have our water, and over here, of course, we have our iodine. So in the procedure 1, we're going to measure out 5 mLs of acetone, 5 mLs of HCl, 10 mLs of water, and finally 0.5 mLs of our iodine. The iodine must be added last because the iodine is the clock, all right? Just like we talked about in the reaction on day 1 back in August. The iodine acts as the clock, and so when the reaction has gone to completion, we will see a color change. In this case, our color will go from a light yellowish brownish color to clear. So let me go back then to the data table. And there we go. And so here we are, reaction 1, 5 acetone, 5 HCl, 10 water, and 5 iodine in that order. All right, so I'll put my goggles on here. And so I need 5 mLs of acetone. There we go. And then we will add 5 mLs of HCl. Okay. And then 10 mLs of water. Okay. Okay, I'm going to go ahead and add those in that order to our reaction beaker, or I should say our reaction flask here, Erlenmeyer flask. And then I'm going to need 5 mLs, yes, of iodine. Okay. Okay. I'm going to get this old stopwatch ready here. Okay. All right, so when I add the iodine, the clock will begin, and we'll see how long it takes for the reaction to go to completion. So, be nice to have a third hand here, but that's okay. Boom, boom. Okay. So, as you can see, and I'm swirling the flask, uh, it is a very lightish, yellowish color, yellowish brown, but it's a very light. I want to see when this thing turns clear. Now, it's kind of tough to do that, so I'm going to kind of use a piece of white paper here to help. No, that helps a lot. So I can kind of look from the flask to the paper behind it and get a better idea of when we have gone clear. It's definitely lightening up some more. We are definitely getting close. I'm going to say we're there. All right. Definitely gone clear. Yep. Okay. For that time, uh, I got 52.03 seconds. However, in this lab, we used class data. This is actually the class data from last year. This is one of those labs where the more data you have, the more accurate and precise it's going to be. And so we used the data from all 6 lab groups last year, combined it, added them up, divided by 6. And for that, it came out to be 49.98 seconds. And so that's the one we're going to go with. Mine was pretty close to that. Okay, I'm going to dump this out, rinse it out with distilled water, and now we will go on to reaction 2, which is now we're going to start with 10 mLs of acetone. Okay. Next, 5 mLs of HCl. Water this time, we just need 5 mLs. Okay. And iodine again this time is also 5. Okay. Again, I'm going to pour the first 3 in the order we discussed. Get the phone ready here. There we go. Clear. All right. Here we go. Going to add the iodine. Clock. Start the clock. Again, mine's a little delayed. Boom. And swirl the flask. Yeah, this one's going lighter, going more clear much more quickly. Boy, we're getting really close. I think we're there. Boom. Okay, I recorded 27.33 seconds. Again, using the class data from last year, that averaged out to 25.09 seconds. Okay, we will clean this out, rinse it out, and get ready to run reaction 3. So now I just need 5 mLs of acetone. Back to 5. Okay. 10 mLs of HCl this time. Okay. 5 water. Okay. And this time the iodine is again 5. Okay. All right. So again, I'll add the first 3 to our flask. Add it back on. Clear. All right. We're now going to get ready to run reaction 3. Again, I'm going to be a little delayed on my timer beginning because I'm missing that third hand. And there we go. Okay. Again, it's a very light yellowish brownish color, very, very faint. And again, it's starting to fade pretty quickly here. Once again, we are getting close, very close. The white paper really helps. We are about there. In fact, we are there. Okay, mine, I got about 28.57 seconds. Class data for last year averaged out to 27.55. I was only a second off. Not too bad. All right. So let me rinse this out. And we will get ready to run reaction 4. All right, so reaction 4, I need 5 mLs of acetone. Uh, 10 mLs this time of HCl again. There we go. Water, 5. Oh, water is 0. Sorry, no water this time. And iodine is 10 this time. There we go. Okay, so I'll add these two. Again, no water on this one. Get the phone reset here. Okay. And here we go. All right. Now this one's a little bit more colorful. The yellowish brown color is more prevalent because, well, we used 10 mLs of it this time rather than 5 as we did before. So this has got more iodine comparatively. So my guess is it's going to take longer for this color to fade. Just guessing, of course. Okay. Yeah, it's definitely has slowed down from the last two. Finally, starting to lighten up now. Getting close. Getting really close now. In fact, I think we're there. Yep, we are. All right, so on that one, I actually got 58.11 seconds. The class average from last year was, let me see, 53.13. So there are our average class times. Now we're going to run down here. We're going to wait on number 5, as the instructions say here. And what we're going to do now is determine the rate of this reaction. Now I'm going to go back up here to the number 5 in our instructions. We calculate the reaction rate by dividing the concentration of iodine by the average time measured. Iodine is the clock, and so again, we're going to be utilizing its concentration as our benchmark for determining reaction rate. So then this then would be, the rate would be the iodine concentration over T, all right? Yes, it's not really delta T, it's just T. All right, so for this first one, our iodine concentration is right here, 0.0010, and our time was 49.9 seconds. So for this first one here, we have 0.0010 molar over 49.98 seconds. And in rounding that to 2 sig figs, as our data is all in, we get 2.0 times 10 to the -5th molarity per second. Okay. Next one, same procedure. Iodine concentration 0.0010. The time here was 25.09 seconds. That works out to be the 2 sig figs 4.0 times 10 to the -5th molarity per second. And the other two would be done exactly the same way. You have the numbers. I'll let you go ahead and do that. Before we run reaction 5, we are going to be able to determine our rate law from reactions 1 through 4. So let's go to the next page, and I will get you started on that. using the concentrations and reaction rates calculated in data table 2, determine the reaction order for each of our 3 reactants. Then determine the overall reaction order and write the rate law. I'm going to do the first one with you, all right? So the first one is acetone or propanone. And so remember, when determining a reaction order, we use our little equation here, C to the X power equals R, where C is by what factor did the concentration change, R is by what factor did the rate change. So how do you do that? Well, we should know by now, to determine the reaction order for acetone, we have to choose 2 experiments whereby the concentrations of both HCl and I2, we have 3 reactants now, that both of those 2 are constant. And if you look back at your data table 2, that happens in experiments 1 and 2. In experiments 1 and 2, the concentration of acetone is changing and the other 2 remain constant. So if we look at those concentrations between experiments 1 and 2, we will see that the concentration of acetone doubled. That is 2 to the X power. And if you look at the rate column down in the lower data table between reactions 1 and 2, we just did that. Reaction 2 was 4.0 times 10 to the minus 5. Reaction 1 was 2.0 times 10 to the minus 5. The factor by which that is changed is also 2. So R is 2, X equals 1. So this is first order in acetone. Okay. You need to do the same thing for the other 2. You need to find 2 experiments whereby the HCl concentration is changing and the acetone and the iodine are not. And then same for the last one. You need to find 2 experiments where the iodine concentration is changing and the acetone and the HCl are not. Once you do that, you should be able to come up with a reaction order for each of these and then write the rate law for this reaction. Of course, we would add these orders up to get the overall reaction order and then write the rate law. Okay? Then, in number 2, it says using reaction 1's data, calculate the magnitude and unit of the rate constant K. So we're going to use reaction 1's data. I'm going to go ahead and write the rate law down here. Hopefully you will have calculated that on your own. This one, as we said, was first order. HCl also ended up being first order, and or hydrogen ion, which comes from the HCl, and the iodine was actually 0 order. So our rate law ended up being rate equals K times the acetone concentration times the HCl concentration, or the hydrogen ion concentration. The iodine was 0 order, so it does not go in the rate law. So using reaction 1's data, so you put the rate in here, which was 2.0 times 10 to the minus 5. You put in the concentrations of both acetone and HCl there, and you solve for K. All right, so that should give you a value of K. Remember, 2 sig figs. And as far as the unit for K, remember that is determined by the overall reaction order. Since our overall reaction order is actually a second order, because this was first, and this was 0, excuse me, that means that the unit for the rate constant K would have to be m to the minus 1, s to the minus 1, where those 2 exponents' absolute value adds up to the overall order, which is 2. And then down here at number 3, using the rate constant calculated above. So now you'll have a K, all right? Predict the reaction rate that you would expect in reaction 5, all right? So you're going to set up the rate law again. Now we have K. You're going to plug in the values of these 2 concentrations from reaction 5, and then you are going to calculate the rate, all right? You're going to calculate the rate. And that would be your theoretical rate. That would be your theoretical rate. Let's go back and do reaction 5 and get our actual rate. I'll just go ahead and plug these numbers in real quick. Just as a reminder, you should already have these down. Remember, this was the adjusted concentration of acetone there was 1.2 molar. HCl was 0.3 molar, 0.30 molar. And iodine was 0.0015 molar. So let's go ahead and do that and see what we get. So we're going to need 7.5 mLs now of acetone. There we go. 7.5 of HCl. There we go. Only 2.5 water. There we go. And 7.5 of iodine. There we go. Okay. Rinse this out real quick. Put in my first 3 reactants. Phone reset here. Okay. All right. Here we go. A little bit longer delay there. I'm getting slower. All right. And it's starting to fade. Not yet, but it's definitely getting lighter. Yep, getting close. Getting close. That's getting really close. I think we're there. Yeah, to set it down on the table on top of the white paper, you can really tell. Okay, that one, I got 32.22 seconds. Our class average, though, was 30 oops, that was up here, sorry. 30.81 seconds up there for our average time in reaction 5. So calculating the rate based on that, we have our iodine concentration 0.0015 over our average time 30.81, and to 2 sig figs, that is 4.9 times 10 to the minus 5th molar. Okay, now that is our actual value for the rate in experiment 5. So as we go back to the calculations, and I'm going to let you finish these on your own. Remember, we calculated the theoretical rate from the data we have in reaction 5. We have our rate law. We have our value of K that we determined here. And so down here, our predicted rate then would be, or our theoretical rate would be plugging those numbers in for K and the concentrations of our 2 reactants in experiment 5 and calculating the rate. That'd be our theoretical. Our actual, we just said, is 4.9 times 10 to the minus 5th molar per second. And so from those 2 numbers, you are to then finish up and calculate your percent error. And I think you'll find that it is very, very close. So I think that finishes up Lab 12.1. I wanted you to see in real time how we go about determining a rate law. First of all, well, determining reaction orders first for each reactant, and then determining a rate law. From that, determining a rate constant value, and then being able to make a prediction by changing up the concentrations to whatever we want to, by making a prediction then of a rate based on those new concentrations. And like I said, as I hope you'll see, that the percent error came out very, very good. So that takes care of Lab 12.1. So until next time, everybody take care and stay safe, and I'll talk to you soon. Take care, everybody. See ya.